When you enter the world of maths, you start comprehending daily lingo as mathematicians do. Really? Don't believe me? Alright, let's try it. When I say the words the polar form, what does it remind you of? This? Maybe even this? Well, by the end of our lesson, it will be something completely different. So, let's get to it. As we know that when a complex number is plotted on a coordinate system, it is called an Argand diagram, where x-axis represents the real part of a complex number and y-axis represents the imaginary part of it. Now, if there is a complex number, for example x plus iota y, plotted in the first quadrant of this complex plane, this means that the point has covered x distance on the real axis and y distance on the imaginary axis, right? Let's name this point A and the origin as O. Now, if you ask someone to plot point A, all they need to do is to stand at O, move x units to the right and y units upwards. That's it. Hence, knowing these two values are enough for plotting this point on an Argand diagram. But, is there a way to locate a point without having the values of x and y? Certainly, and that requires two new quantities. First, the distance between the point and the origin, represented by a line segment and denoted by r. Second, the angle formed by this line from positive x-axis called theta. Notice how this angle varies if the position of point varies. Similarly, the distance r also has different values for different positions of the point. Do you get what I am trying to say? If I tell you that a point lies 5 units away from the origin and the line joining that point to the origin makes 30-degree angle from the positive x-axis, then you can easily plot the point without even knowing the coordinates, right? So, we conclude that a complex number can also be represented in terms of these two variables, r and theta, instead of real and imaginary coordinates. This form you see on the right is called the polar representation of a complex number. It is an old concept with just new variables. Now, there exists a mathematical relation between these forms that allows the conversion between rectangular and polar representation. For that, we need to focus on this triangle, which happens to be a right angle triangle due to 90-degree angle at M. Hence, the Pythagoras theorem is applicable here. Once the base perpendicular and the hypotenuse is identified, all we need to do is to substitute the values. And bingo! We have found the value of r in terms of x and y, which, if you are a good observer, is nothing but the modulus of a complex number that we have already covered in the previous session. Now, to find this angle theta, we will use trigonometric identities. Sine is perpendicular upon hypotenuse, cos is base upon hypotenuse, and tan is perpendicular upon base. Substitute these values from our triangle and we get y equals to r sin theta and x equals to r cos theta. Looks like we have found x and y in terms of r and theta on the go, but we still haven't found theta yet. Not to worry, the tan function is still here. Just take its inverse and we get theta as well in terms of real and imaginary coordinates. That's it. We have acquired all the required tools for the conversion. R as x and y, which is nothing but the modulus. Theta as x and y, also called the argument of a complex number. The values of real and imaginary coordinates in terms of r and theta. Now, how about finding the polar form of a complex number when its real and imaginary coordinates are given? But for that, my friends, stay tuned for our next video.